Since the dawn of the computer age, the size and performance of electronic systems has improved by many orders of magnitude. Each new generation of process technology is smaller, faster, and more power efficient. Now this is under threat. Fundamental physical limits mean that further progress cannot be achieved without sacrificing consistency and reliability. A gap is opening up between the theoretical performance and the conservative operating limits that are needed to guarantee functionality over all conditions and manufacturing variations. In the Prime project, we seek to close this gap by making systems self-aware and adaptive. For example, we can adapt to the deterioration caused by aging by measuring and responding to performance changes as they occur. We have implemented an FPGA-based video processing algorithm with real-time performance sensors, which are transparent to the functionality of the circuit. These measure timing slack, which is a safety margin present at the end of every clock period. With the use of a closed-loop controller, we can adjust the voltage and/or frequency of the circuit to optimize the amount of slack so that the circuit is reliable but not wasteful. Here, we've just begun running the video processor. In common with many systems of this type, it needs to process data at a certain rate, but we want it to do so as efficiently as possible. The clock period is set to a nominal 188 MHz. The circuit is initially powered at a safe 1.1 volts, and a large surplus of timing slack is measured. In response, the controller gradually steps down the voltage, reducing the amount of slack to an optimal level, eventually reaching 1.06 volts. As it does so, the power consumed by the circuit is reduced, and there's an overall saving of 67 milliwatts, or 32% when compared to running the circuit under nominal parameters. The controller is quite simple. Timing slack is measured at fixed intervals, and the voltage is incremented or decremented accordingly. Additionally, the throughput requirements of the system might change. For example, if the video resolution or frame rate varied. When this happens, the controller consults a table of known safe operating parameters, and then begins fine-tuning as before. The operating frequency has now been increased to 210 MHz. To operate at this speed, a higher voltage is needed, so the controller initially selects 1.2 volts to guarantee reliability. In the current operating conditions, this introduces a surplus of slack, and the controller once again seeks to optimize this, gradually stepping down the voltage. This is just one example of an adaptive system exploiting real-time performance measurement. Other applications may not have fixed throughput requirements, but instead need to maximize throughput under varying voltage or power constraints. It is important that these systems remain safe, and this is why residual timing slack is maintained. If the device slows down due to, for example, temperature or aging, timing slack will reduce, and the controller will respond, returning it to a safe level. This allows adaptive systems such as ours to be both more efficient and robust than their conventional counterparts.